Guys, you are welcome again to the continuation of our tutorial series on Python tree data structure. Uh, the essence of this tutorial series is for us to be able to understand the logic of programming, not to cram the codes. And these are very two different things. When you cram a code and you don't necessarily understand the logic of that programming, when the problem is twisted a little bit, you get stuck forever and you can't find your way out. But when you understand a code, you understand the logic behind the coding. Even if you cram the code, when the problem is twisted slightly, you can use the previous knowledge of the code that you know well to adjust yourself to write the solution for the twisted code. It's very important. That is very important. Remember the last time we talked about finding the minimum in a tree, and we went through the logic of how actually we needed to introduce this current and how we need to continue to update this current. So today we shall continue on the basis of that to build more on it. And I must say what we have to learn today is a bit more tricky. But we'll see how we can try as much as possible to simplify it. It is how to insert nodes into a binary search tree. Now, to insert a node into a binary search tree, you want to ensure that you have not broken the rule of the binary search tree. To ensure that everything on the left of a node is less than it, and everything on the right of a node is greater than the node. That is very important to maintain that structure. Alright. So having said that, let's now say that we want to insert a node to this particular insert a node to this particular tree. So let's say the node I want to insert, we want to insert a node to this tree, but then we don't know where exactly we should insert the nodes, because the node can come in into either here or here or here or here or here or here. You know, we already established the fact that these nodes satisfy the binary search tree. Okay. So, if you want to insert the node, a new node, so these are a new node waiting to be inserted, we have to start from the root node. So we must have a reference to the root node. Then we compare first, we check whether this root node exists. Every tree must have a root node, even if it is none, but it has an attribute called root node. So we check whether the root node is in existence. If the root node is not in existence, that is the end of our program. We just make our root node to be equal to the new node. And that is what is happening here in the first place of insert node. Okay, so I think for me to be able to keep this, now let's just use this, so this one. Okay, so we are now talking about the insert. So we see it in code. We want to insert this data. We wrap up this data in a class, in an object called node. The reference is node. So the first thing we do is just this one. If the root node, which we already have here, this attribute, if it is none, that means we don't have a substantive root yet. If that root node attribute is none, then whatever node that we are inserting that has been wrapped up inside this variable automatically becomes the root node. That's easy to understand, right? So that's what's happening here. This new node, you compare, first of all, check the root node. If it does not exist, then just assign the root node attribute to this new node. That's the end of the operation of inserting. But then, if this root node is not none, okay? So if this root node is not none, then you want to compare the new node with the root node in values. Then if the root node, if the new node is less than the root node, then you know that the new node should go to the left of the root node. And if the new node is greater than the root node, you know that the new node should go to the right of the root node. In this implementation, to keep things simple, we just ignore when they are equal. We ignore duplicate. Now, but when you have to now implement this in code back, all right, so when you now need to implement this in code, then the logic comes in again. You have to now introduce these two variables called current and called parent. Now it's easier to see it in this code because we've already introduced it and we've fully tested it. But let's assume you don't even know. How do you just begin to just introduce current variable and parent? Let's go through the naive way that we will have tried to do it. Okay, so the naive way we'll have tried to do it is to say, okay, I will now take this root node, then I will now say root.left. I compare it with this. Let's assume it's less. Okay, so do I now make the root.left to be equals to this one? Not quite, because this might not be the last node. You might still have more and more. Okay, then I will now say, okay, if that root.left, which is this one now, is not none. Okay, yeah, so it's not none. That means I cannot insert this one into this position. Okay, okay, I've tested that this is not none, that it exists. So what do I need to do? Then I have to get this one again, root dot left, or what do I do? Or I store root dot left inside a variable. Okay, let's say I store it inside a variable, call it n. Okay, so I will now say n equals to root dot left. Okay, that is referring to it. Remember, this is root dot left. You put it inside a variable n. Okay, then I will now say compare n with the new node. All right, that's cool. So when I now compare n with the root node, let's assume it is less. Okay, so I know it goes down. Okay, so do I just say n dot left is equals to this one, because this is now my n? Okay, so n dot left will be this. Do I say n dot left is now equals to this? No, not quite. There's something here. Okay, so what do? I compare n and say, okay, if n does not exist, which is this. All right, okay, so if n does not exist, what do I do? Oh, okay, I put it there. Yes, that answer. What about if n exists? Or if it exists, then I have to get n dot left again. Oh, I have to get n dot left again. So if I have to get n dot left again, so I need to test whether what is here exists. So I will now have n dot left dot left. Has just become difficult to track. So it means that you want to keep putting the every node and creating a variable for every node, and this node can just continue like that, and you don't even know how many nodes will be on this left. So you just give, say, okay, n1, n2, n3, n4, n5, and so it won't work that way. When you begin to run to that kind of problem in programming, then it is time to think otherwise. That, okay, I need to introduce another variable. That's the best way. I find it personally easy to understand. When you begin to run into a problem that is becoming intractable, that's the logic. That you keep having to keep assigning variable, then you have to stop and go back to the beginning and introduce another variable. You see it in a lot of programming context, programming problem, and it takes quite some practice to be able to get used to it when you are writing a program for a fresh problem that you don't know the solution. So you discover that you need now to introduce another variable called parent, whatever you like to call it. So you make that parent to be none, which sounds interesting, because if current is your root node, the parent will be none. A root node does not have a parent. Let's leave out this while true for now. Let's concentrate on what is inside the while body. Because when you're writing a program, it may not be obvious to you that you need a while loop forever. So you now say parent equals to current. Why are we saying this parent equals to current? That's the programming logic there. You need the parent and the current to point to the same node. You need the parent variable, I repeat myself, you need the parent variable and the current variable to point to the same node at some point. Then you will now use the current to traverse through the nodes until you get to a particular point when that current becomes none. When that current becomes none, you will now use the parent to insert the node, because parent and current were initially the same. What you are interested in is to put the new node at the left of current, but you have copied that current inside parent, so they are referring to the same node. So at this point, current left is the same thing as parent left. But while you use this current to be able to traverse through the tree, you will have messed up with current in your update. So at this point, for instance, you have messed up with this current, it's no longer equals to parent. So if you come here and you say if current is not known, and you say current dot left child equals to no, you will be saying something drastically different from what you intended to do. But because you have copied your current into parent, now that you have messed up with this current, you can use that parent to be able to do justice to your intention. You may want to pay some attention to think through that. You will see it a lot, where you need to have I, J, K variables to be able to keep track of things. You will see the same thing in insertion sort. You will see the same thing in quick sort. You will see the same thing in match sort. You see it virtually in writing functions to solve problems, where you have to keep track of some counters and some variables, and you have to at one point in time make a copy of a variable, use one variable to do some findings, and once you are able to get the finding and you need to take an action, then you now call your copy to be able to make that action. It's a very important programming construct. So we use the node because I find this I read a lot online about code. I just see the code, but when I'm to write a similar code, I just get stuck. But I understand what they did, but when I'm to write the similar code, I get stuck. My problem was I understand the code to that problem, but I don't understand the code generally. I don't have a full understanding of the logic of solving problems with manipulating variables, manipulating counters. That's the problem. That's why I'm spending so much time to explain this logic. Once you get the logic, then you can write just any program. It becomes just a matter of practice. So we can go back now. So what does this now do? You make the parent and the current to be equal. You can call this thing any name you want, but it makes a better understanding to use parent, since the parent of the root node is none. So you now, the data you want to insert is this. You compare the data you want to insert with the current data. Don't forget, current and node, they are both objects, and inside them is wrapped the attribute data. So you compare them. If it is less, then you go through this block of code. If it is greater, you go through this block of code. That explains things at a high level. So we see two branches there. So let's now take one branch. If the data in the new node I want to insert is less than the current node, what do? we make the current node to take the position of its current dot of its left child. So we update current to become current dot left child, just like we explained with finding minimum. So by doing that, we have moved down a little in the level. So when we were here, this is current before. When we now update, the left child of this current is this. So we now say our current now is now current dot left child. So our current is now this one left child, which is this. So this becomes our current. By doing that, we have moved down a level. Don't forget that this is level 0 in tree. This is level 1. The whole of this. The whole of this is level 2. The whole of this is level 3. So on. So we have moved down. So by doing that update, we are able to move down the level. And by the time we start solving problem that has to do with a level, you will see that you may need to do some additional operation in this level. When you have to, for instance, if you are given a problem to sum up all the nodes at each level, or you are given a problem to find out the maximum node at every level, or you are given a problem to find out which level has the highest node. A lot of problems that you can come in, but once you understand this, then it becomes easier. That by updating this current equals to current dot chart, you drop down one level. You drop down one level. So you have moved down level. So once you have dropped down a level, you are not at a potential node that you can insert your new node. So you now say, okay, if that node is none, then you have gotten to where to insert it. Alright. Then you can say parent dot left child, which you have copied here, to be equals to node, which is your new data. But you may ask a question, what about if this one is no longer none? Then you have to go back iteratively again, start all over again to be able to drop down. So this will now make the while loop comes to your reality that, okay, I need something that will be looping forever. So you can now just wrap all these codes inside a while loop. Because if this is now none, then you need to go down a level again. And to be able to go down a level, you have to start all over again. Because this is where you will be able to go down a level. So let's look at it here. So if this becomes our current now, because we have said current dot left is now current, so these are current. Remember, this is still the parent. Okay, so I now come here and I say, is this current none? No. Then I have to go down this level. So in our code, it will be starting all over a while loop. Then what will happen? My parent will now be initialized to this. So at that time, parent and current will become this. And I will start over again and they say updates by saying if this new data compare with current data, which is this. If it is less, then I look towards this left direction. That is where I will insert it, but not quite. So I will now update the current. I will check if this current dot left, this is our current. So if the current node dot left, just like we have it in the code, so this is our current. So we are now here, we check if the node dot data is less than current. Okay, so what do? You make the current, the new current, to be equals to the what? The current dot left child. All right, so we are now here, parent and current is this node. So if you compare this node again with the new node, so current dot data compare with new node dot data, if it is less, then what do? You make current now to be equals to, you update your current to be equals to current dot left. So your current moves away from here and comes here. So current is no longer equals to parent. So you now say if this current is none, that means it does not exist, then you insert your new node here. But to be able to insert your new node here, you have to now call this parent dot left. So parent dot left will now be your new node. You cannot say current dot left because this is now your current. Okay, so it's now the parent dot left will now be here because this is where you want to insert. But if you come in here now, you say, oh, this is not none. Okay, you have to go down again the while loop to be able to update and go down a level. So you go down a level, then you start again. You make parent will no longer be this. So this will now be parent and this will now be current at the same time. So you now use this current and compare with the new node. So current and the new node, is it less? Let's assume it is less. Okay, you know you have to go into this direction. Then you will now make what? Your new current to be current dot left, which in this case this does not exist. So that means your current will now become none since that does not exist. So it becomes none. Alright, so then you now say if current is none, then you update parent dot left, which is this, to be equals to the new node. It takes some time to be able to grasp that, but if you give it time over and over again, it begins to come to your understanding. That's it for now. Thank you for listening. In the next tutorial will demonstrate that. Thank you for listening, and then see you in the next one.